Now we're going to look at RLC circuits. This is really pretty optional. It's not in the main flow of the videos, and I'm going to go over it pretty quickly. But it's a great place to look more at deltas and even like delta primes, things like that. The reason for that is in a circuit, things like quick on-off switching, essentially instantaneous on-off switching, voltage and current spikes, and just in general any kind of fast transients are really realistic, that we are often interested in the behavior of a circuit over a time scale of seconds or minutes or hours, but certain things are happening in that switch that could happen in microseconds. And it's very reasonable to model those things as deltas, and in fact delta primes, and maybe we'll go even one more derivative. So for me, it's a good place to get more intuition about these guys. That's really why I want to do this. Okay, so we have our standard RLC circuit, an external voltage, an inductor, capacitor, and a resistor, although we're going to throw that away in a minute. And we have our standard equations based on Kirchhoff's laws, really just adding up the voltage drops around the circuit. And then that really refers to the charge on the capacitor. So Q is the charge on the capacitor. That's one variable we could use. But then I, the current in the circuit, is a more common variable. I'll use a capital I, which isn't super standard for electrical engineering, but it's better for math. And that is going to have to do with the derivative of E. One of the things that's going to get us is an easy way to be forced to talk about things like a second derivative of a delta function. That's one reason I want to do this. So, and as usual, we're going to start out with nothing happening long ago, and then usually what I'm going to go through some examples, as in the PDF, and just think about what happens if various different things happen at time zero. More and more extreme things happening at time zero in all the scenarios. So there's our setup, and to make it simpler, we're just going to set r equal to 0. Not amazingly physically realistic, but it doesn't make it too weird to analyze, and it makes the math simpler. We've been doing that pretty consistently, taking out any kind of dissipative or damping term. And it's up to you to put that back in at the end if you really want. Okay, so let's look at a first example. It's all going to be based on different choices for forcing. Although, first of all, let's remember, just like in the mass spring system, the natural frequency, when I take out the resistance, it's going to be something that has its natural behavior is going to be just periodic, and the natural frequency is 1 over root LC. So again, if that's not familiar, good opportunity to review that in a standard differential equations book. So let's look at E1. Our first choice for our forcing function is going to be, I'm going to just draw the graph first. Let me see. We have a good space for graphing here. So our E1 is going to be like this. And so it's nothing, and then I turn it on as a ramp. And so that's going to be the turn on, h of t, times kt. Notice that to make the units work out, k has to have units, say SI units of volts per second. It's a good double check in other answers that we'll get later. And then we want to guess, first of all, what should Q of t and I of t look like? Okay. Well, this isn't the most radical thing to do right here at the start, so they're probably going to be continuous. Remember, to go from that external forcing to Q, it's essentially two integrations. This guy is continuous, so this guy should have at least one, maybe two derivatives that are continuous, and even I should have a derivative that's continuous. So, and then what's going to happen? Well, I slowly turn on that voltage higher and higher and higher and higher. Apart from any oscillatory behavior that's happening, if this voltage gets to 1,000,000 volts, something's got to balance that, and the inductor isn't going to do it. Not sort of in a constant way. It can only produce a voltage when things are changing. So there's got to be a growing charge on the capacitor. So Q's got to grow and grow and grow and grow, but then that's going to be superimposed on some sort of oscillation that when you hit any kind of oscillatory system with a sudden change, it's going to resonate in some way. And then the I, so this is going to be something like, nothing, 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 and then wiggle, wiggle going up. The I should be something like nothing, nothing, and then it's got to wiggle, but with a bias towards putting more and more and more charge on the capacitor, so it's going to be up here. And that's exactly what we would expect from just a linear growth in this guy. And therefore, note E1 prime is a step function. And that's the one we'll analyze first. In some of these cases, the Q equation is a little easier to think about. In some of them, the I equation is a little easier to think about. It's good to think about both of them. They're just derivatives of each other, of course. Okay, this one is just a derivative of that one. So let me get a little more room by erasing that. Okay, so what do we got? We've got L I double prime plus, and then I'm going to use the omega here. It's just L omega squared I. So I'll focus on the I equation first. And that's that E1 prime, and that's just KH. All right, it goes from this guy, the E goes from slope 0 to slope K, and so E1 prime goes from height 0 to height K. Okay, and I don't want to have to do that over again. This is exactly something we did in the first videos. It's not hitting with a hammer, it's turning on a constant force. So sort of taking the mass spring system and then suddenly turning on just a constant force. And we know what the solution of that looks like. I think we'll erase this stuff. Try not to erase this though. Okay. We know that I of t turns out to be, and I'm going to put in the constants. You can check the constants if you're worried. Okay, it's going to have something to do with cosine omega t. It's going to turn on at 0. But then that 1 minus is what flips it up, and so that's going to be, as expected, something that's oscillating like this. Okay, so that's I. And then the integral of that, so Q of t is just going to be the integral of that sucker. And so it's just going to be t minus 1 over omega sine omega t, and of course all starting at 0. And without, maybe this will be kind of a busy graph, but as expected, so t just goes up linearly, and then the t minus the sine t gives you the wiggle going up. If you take the derivative of this, this goes between this, the minimum of this is 0, because the derivative of this guy is, the omegas cancel out, you get cosine, and so the minimum derivative is 0, which is of course what we've got here. We've graphed the derivative of the function, that's the I. So the charge in the capacitor starts wiggling up here, and it never goes back. The charge in the capacitor never decreases in this scenario. Okay, so that's kind of a warm-up because we didn't need any distributions here. A cool fact, something I mentioned in the PDF, is if you look hard at these, just let's let t greater than 0, so these are 1. If you look hard at these are actually the equations for a cycloid. If you do a phase portrait, which is always a useful thing to do in differential equations, a quantity and its derivative, or essentially, or two interesting quantities that vary together in a second order system. Sorry, a second order equation, or equivalently a first order system of differential equations. You can look at the phase portrait for this guy, and for this one, it's a cycloid. The Q is constantly increasing, and the I is big 0, big 0, big 0. So that's just cute. I bet there's some electrical engineering thing that makes more of that, but I don't recall ever seeing that observation before. But it was cute just to realize that was coming out of the math. So now let's take it further and try to take distributions, try to see how distributions come into this. So next stage would be the voltage suddenly turns on. So we started out with a closed circuit with no source, and then we turned on a source. Okay, so this is number 2. Okay, so let's see. Let's graph. So E2 is now like this. Okay, E2 prime, let's go ahead and write that down. E2 prime is going to be K delta. Aha, so distributions are definitely coming into it if we insist on thinking of the current equation, which is fine. Okay, and then what about our guess for I and Q? Okay, so it turns on at a fixed voltage. We shouldn't get accumulating charge on the capacitor. Okay, and so but we need to have the charge on the capacitor be biased. That looks familiar, but that's going to be Q now. Okay. And then it's going to be biased in one direction to balance out that fixed non-zero voltage on the input voltage. And then the derivative of that guy is just going to be symmetrical. It's going to be something like this. Ooh, let's see. I want to max out here, like that. Okay. Just going to be a sine wave, one would think. Okay, so let's make sure that's true. Once again, this is not new stuff. Okay, we've got L. I'm going to go ahead and do the I equation because it's our favorite thing ever. It's hitting the mass spring system with a hammer. Okay, so we know the solution of that sucker. So that's going to be K. And again, you can check the constants, but the big observation was this is exactly what we got. We got nothing and then suddenly a sine wave. And with the right constants to get the normalization right. If you want, that's K root C over L, if you don't want the omega in there. Okay. Okay, so the main thing is we can just write that down with, as long as we get the normalization right, because we have done this equivalent system hitting a mass with a hammer. If you look at Q, okay, you can just integrate this and you get an omega coming down, L omega squared. All turns on at the origin. And you have to get the initial condition right. This does need to start at 0, so that's where the 1 minus comes from. Okay, so that strategy would be refer to previous work and then integrate. But of course, the easiest strategy in this case is to realize that this is just the derivative of the previous. And so the I is also going to be the derivative of the previous case. And I want to justify that a little more carefully in number 3. It doesn't take much justification, but I want to talk about, there's something special about this equation that lets us do that. Okay? And so that's why these were so familiar. That the new Q was the old I, and then I is just the derivative of that sucker. So that's why Q here was something that was exactly what we saw before. So, okay, so let's just look at it qualitatively though before we go to number 3. And I think actually I'll do number 3 in the next video. Does it make sense? We turned on the voltage, and the Q equation responded in not a very sudden way, not a very dramatic way. It's still two integrals of a discontinuous function, but something that's not a delta, and it just sort of starts in a very reasonable way, starts oscillating. The I is a little bit more interesting, that it actually has a non-differentiable point here, that somewhat suddenly the current has to start when we flip the switch. Okay, but hopefully that's intuitive from a basic understanding of circuits. All right, we'll start with 3 and go through the rest of it hopefully in the next video.